In our previous example, we saw we took two summation of force equations and one summation of moment equation to determine whether or not our system was in static equilibrium. We can replace one of these summation of force equations with the summation of moments equation. That is, as opposed to taking the summation of forces in our y direction, we could potentially take our moments about point B or C. That is to say, we would have a new dependent equation, and thus we could have three equilibrium equations that can be applied to our two-dimensional system. These equations are the summation of forces in the x direction being equal to 0, the summation of moments about point A being equal to 0, and the summation of moments about point B being equal to 0. The key to this is B cannot lie on a line parallel to the y-axis that passes through A. That is, if we drew a line through A, our moments about point B, i.e. point B, cannot be on that line. Now, these first two equilibrium equations indicate that external forces must reduce to a single force that acts in the vertical direction at A. Our third equilibrium equation indicates the single force must be equal to 0. In example 2, we want to repeat example 1, however, we want to replace our summation of forces in the y direction to a summation of moments about point B. To begin, we'll cast our summation of forces in the x direction and set this equal to 0. This equilibrium equation remains unchanged, and we are able to solve for Rax. We'll also take our summation of moments about point A and set this equal to 0. We see RBY acts on a moment arm of 2L, PX, QX, and SX acts on a moment arm of L, and these two contributions create a counterclockwise rotational tendency. We see QY acts on a moment arm of L, and SY acts on a moment arm of 2L, creating a clockwise rotational tendency. Thus, our summation of moments about point A being set equal to 0 gives us 2L RBY plus L times the quantity Px plus Qx plus Sx minus L times the quantity Qy plus 2Sy, and this is equal to 0. Thus, we can solve for RBY. Now, if we take our summation of moments about point B and set this equal to 0, we see that Px, Qx, and Sx act on a moment arm of L, creating a counterclockwise rotational tendency. Qy acts on a moment arm of L, and Py acts on a moment arm of 2L, creating a counterclockwise rotational tendency, and Ray acts on a moment arm of 2L, creating a clockwise rotational tendency. Thus, our summation of moments about point B set equal to 0 gives us L times the quantity Px plus Qx plus Sx plus L times the quantity Qy plus 2Py minus 2L times Ray is equal to 0, and thus we can solve for Ray. We see we can solve for Ray, RBY, and Ray, all independently of our given equilibrium equations. In example 3, we want to reconsider example 2, where we took the summation of forces in the x direction, the summation of moments about point A, and our summation of moments about point B. But in this situation, we want to replace our summation of moments about point B to our summation of moments about point C instead. In doing such, we will show that we will construct a system of equations that does not allow us to determine the conditions for static equilibrium. That is to say, since point C lies on the vertical line that passes through point A, it will be an invalid equilibrium equation. In repeating example 2, we see we have the same summation of forces in the x direction equation. That is, Rax would be equal to Px plus Qx plus Sx, and we can solve for Rax directly. When we take the summation of moments about point A, we arrive at the same equation we had before. 2L times RBY plus L times the quantity Px plus Qx plus Sx minus L times the quantity Qy plus 2Sy. We can solve for RBY directly from this equation. If we take the summation of moments about point C and set this equal to 0, we see that Ray does not contribute, but Rax and RBY do. We would have Rax acting on a moment arm of L, that's going to create a counterclockwise rotation, RBY that's acting on a moment arm of 2L, that's going to create a counterclockwise rotation, and we'd have Qy and Sy acting on a moment arm of L and 2L respectively that are going to create a clockwise rotation. Thus we would have L times Rax plus 2L times RBY minus L times the quantity Qy plus 2Sy being equal to 0. We see from our summation of forces in our x direction, we already have an expression for Rax. And we see from our summation of moments about point A, we already have an expression for RBY. If we substitute in our expression for Rax from our summation of forces in the x direction into our summation of moments about point C, we would see we'd have the identical equation for our summation of moments about point A. That is, we'd have L times the quantity Px plus Qx plus Sx plus 2L RBy minus L times the quantity Qy plus 2Sy is equal to 0. That is, we have two equations that are the same. We only have two independent equilibrium equations, which will allow us to solve for Rax and Rby. We are unable to solve for Ray, for we do not have an equilibrium equation describing it. Since Ray was neglected from both our summation of moments about point A and our summation of moments about point C, we cannot solve for it. As opposed to having two summation of forces and one summation of moment equation, or one summation of force and two summation of moment equations, we can also have three summation of moment equations. That is, we could take the summation of moments about point A and set this equal to 0, the summation of moments about point B and set this equal to 0, and take the summation of moments about point C and set this equal to 0. The key to this formulation of equilibrium equations is that the points A, B, and C cannot lie in a straight line. Now, our first moment equation requires a singular force acting at point A. Our second moment equation requires this force to also pass through point B. Our third moment equation also requires this force to pass through C. Thus, that force must be equal to 0.